So, bonjour, je m'appelle Daniel, j'étudie NSU, and I'm currently studying on the Department of Physics of Technical Informatics, and I would like to present to you my coursework, the automation of a test stand for undulator power source. Yes, that's a mouthful, but I was wondering.
It doesn't work.
Okay, so we've all heard of SCIF, right? The Siberian Ring Photon Generator. It's a nuclear accelerator where they have a beam of electrons going in a circle at very high speeds. And so when they turn down the angle, it emits photons and it hits a special target, which allows us to study this object at the molecular level. My coursework goes about powering this nuclear accelerator. To control the beam, to focus it, and to have it going at the right speed, you need a lot of electromagnets. To control these electromagnets, currently the Institute of Nuclear Physics is using two powerful generators, current generators, of up to 700 amperes, but that's not enough to calibrate each individual one. That's why we need up to 2,000 more additional, smaller power generators that will help in assisting in calibrating and controlling each individual electromagnet. And since that's a lot of electromagnets, the Institute of Nuclear Physics is currently unable to produce them all. That's why they're currently looking on the market for a substitute. And so the goal of my coursework is to write a program with a simple interface that will be able to test these power generators that we got from the market and see if they are sufficient for our goals. And my project is built on testing the ITEC ITM313D power source. So, the methods. I wrote a program on using Python, the language Python, with the libraries Qt for the graphics interface, socket object to connect through the router, through the internet connection to the devices using their IP addresses and port numbers. So this is the power generator, which is connected with an Ethernet cable to the router. And this is the multimeter that we are testing the precision of the power generator, which is also connected via cable to the router. My computer is connected to the router via standard internet connection. So, and then the results were tested using the library Matplotlib. To command the power generator and the multimeter, I use the standard command standard SCPI, which is a standard. It's not a programming language, it's a standard. Each device has its own individual language, but the rules of this language are the same among the devices. So these are the results of my coursework. On the first column, we can see this was a constant current set for several hours. We can see there's a temperature dependence because the longer it goes, it seems the more it heats up, and so that's why the temperature seems to be, not the temperature, the current seems to be falling. But why exactly, which device has this temperature dependence, we haven't figured it out yet. It's puzzling everyone. On the second column, we see a linear function. The step is because of the program, because of the time measurement, and we see a sine function. And so these errors, you can see there are 5 to the power of 10 minus 5 to the multiplied by 10 in the power of minus 4 amperes, which is a very small error, which is quite sufficient for our needs. And so in conclusion, I was able to write a simple program with a simple interface, which allows the tester, the engineer, to quickly, precisely test the power generator with several functions and be able to measure the results from the power generator, from the multimeter, and if needed, write this collected data to any specific file that he writes in the needed space. That's all. I believe Honest and Gabeness said no questions, right?
But let's keep the question brief.
Why are there only two types of signals? You open the final slide. Final. So there is two types of signals, linear and sine.
And a constant current.
And constant. And what?
Those are the requirements that they gave me. That's all they need to test these power generators.
Okay.
This is not an end program to be put in to control the nuclear accelerator. This is only to test the power generators.
I have a question.
Yeah, first.
Right.
You wrote so complicated program, but why you don't implement lower indices in your interface?
What?
Why you
Spaces.
yeah, without spaces, without low indexes, you just when you highlighted the current E0, no, right side. E0, EF, why you just
Well, it's explained in the instructions what these measurements, what the numbers mean. I can explain right now in detail, but that will take a lot of time.
I guess that's not necessary, thanks. Thanks a lot.
Денис? Normal.
No,
No question?
no, just one, remember, one question.
Wow, I'm kind of nervous.
Don't worry, you can do everything.
My work is connected with the mechanisms of extinguishing the excited states of L and D isomers of tryptophan as part of the model J8. First of all, we need to get more information about the Alzheimer's disease and its stages of formation. First of all, there's accumulation of D amino acids through the life cycle of animal or human, and it also can be caused by the radiation of the sun and something like this. These D amino acids reduces functional activity of protein by damaging its fourth and third structure, so they cannot work properly in organism. Then beta amyloid composition comes and it leads to the formation of beta amyloid 42nd, which is really toxic for the organism. It appears under the action of enzyme, also called gamma secretase. A few more stages and information about amyloid theory, which is also can cause the Alzheimer's disease. First stage is mutation of beta amyloid precursor protein under the influence of gamma secretase. Then it goes to the beta amyloid 42 and its accumulation. These plaques can cause real damage to the brain cell and its synapses with oxidative damage and activation of altered kinase and phosphatase, which can cause death to neurons and death to human. Well, a few words about my work, why it is important. First of all, we need to study homoheterality, why it appears and how dimers can change its structure through the life cycle. Then the problem of practical medicine, because NSAIDs, non-steroidal anti-inflammatory drugs like ketoprofen or something like this, influence on our organism, like L and D isomers can influence in a different way. Why cannot one of them cannot be used to cure but to damage? And the last one but not least, the gamma secretase in high dose NSAIDs can be tested as inhibitors. So that's why we need to study the process of processes that occur through donor and acceptor interaction in those D8s. It's important. Well, there are a few hypotheses that we need to prove. First of all, is how the process work between L and D tryptophan. with NSAIDs. There is also hypothesis of dimer formation through the process of donor-receptor interaction. We also need to show the difference in efficiency of homo and heterodimers through the CIDP. I used methods that is called nuclear magnetic resonance. It's an observation of absorption and emission, which can be shown through looking at these pictures. These methods can help us to find out the interactions between spins, which can also be used to understand the formation and better understanding of the whole structure of protein. Another method is chemical polarization, and with this method we can study radical reactions. This is my experimental setup: spectrometer, light source, and ampoules, which are pretty base. I prepared stock solutions to minimize errors with a different concentration ratio. This is the concentration of SS isomer, and there's another like SR dimer. On this scheme, you can find on this scheme you can find ketoprofen and tryptophan, and all peaks are matched. All protons are matched to its peak. You can see it on the spectrum. These spectras can show us different concentrations, and they are studied on NH protons, on tryptophan. You can see CIDP, like NMR. The first spectra is NMR, and the lower is CIDP. The left one is SS, and the right one is SR in each spectrum. This is the equation that we used to find the relationship between polarized and unpolarized spectra and the concentration of biradical zwitterions. This slide shows the dependence of the amplification factor. This K is like that amplification factor. And on this slide we can find the correlation between the concentrations of dimers and the factor. To sum up, we found out that there is a difference in efficiency of intermolecular electron transfer in optical isomers. It can be occurred because of the spin density distribution, and another one is the dependence of the amplification coefficients connected with the difference in concentrations, which we can see on this slide, and also this concentration graph can be approximated by the model that can show us that there is a formation of dimers in our process of CIDNP. Also, the CIDNP efficiency is higher in heterodimers than in homodimers, which is shown on that slide. Like SR peak is lower than SS peak. That's all. Thank you for your attention.
Isn't it more about chemistry than physics?
Well,
Like physics methods, right?
it's spin chemistry. Spin is physics, you know.
Oh. Okay.
Great, thanks.
That's all.
Thank you.
And guys, can you please stand closer to the screen if it is possible, okay?
Okay. Thanks. So
So the topic of my presentation is the study of traumatic brain injury of the Daniel radiofish using Nissl staining method. So firstly, what is brain? The brain is an organ of the nervous system. It's actually the major part of it, and it mostly consists of neurons. The neurons are the biological cells that can store, transmit, and gather information. And well, on the slide you can see the common causes of the traumatic brain injury, and the TBI is basically like mechanical damage to the brain. And the thing is that the process or the pathogenesis of the disease is not always the same. It depends on the type of damage, and that's why the scientists have been concerned about this topic, and there's no one cure to this, and or a certain treatment method. So we need to know more about the TBI, and apparently we can't use human to study the traumatic brain injury, and we use the model organisms, and here are the most important ones. And in my study I used the zebrafish. So in one of the aim was to study the existing methods to bring the TBI to zebrafish. Also learn physics of the setup that is in my lab. Also, one of the aims was to estimate the extent of neuron destruction based on the laser exposure time. And how did we determine the damage extent? Damage of the brain. So firstly, here's the experimental setup. So the laser being targeted to the fish's brain, and it's the time that, so the beam focused for either 0.5 seconds, 1 second, or 1.5 seconds. And how we estimated the damage was, so we used Nissl neuron staining method. We took the aniline dye, we dyed the samples using it, and then we washed the sliced samples of the brain using alcohol, and then all the neurons, everything but the neurons were washed away, and we could see the stained neurons. So here are the pictures of what we got. So the blue refers to the neurons, and so here's we observed it in the microscope, and here's a closer look to this. So here you can see the healthy neurons, not the healthy, the neurons of the Schnepp group. So these are the neurons of the fish that were damaged, were damaged, and then we observed their brains in 30 minutes. And here are the, so these are the neurons that exist, that live, and these are the neurons that that are dying. So basically the arrows shows them. And, well, as a result, we learned the physical principle that explained the damage to the brain. However, the results are not that promising because, well, the samples that we got were overdyed, which means that we can't really say how the duration of the laser exposure affects the neurons, because even though we know the theoretical layouts, and we still can't say how it influences. But, well, in conclusion, in future we plan to use another analysis, immunohistochemical analysis, that would tell us, that we hope would tell us more about the damage of the brain. So, thank you. Yes.
Can I ask a question?
Okay.
Just a simple question. Where do you get so many zebrafishes?
Well, one of the advantages is that they're cheap and it's easy to store them. Like, so it's not a problem. Like, it's not like rats or mice. They're actually hard to watch for them and expensive. Well, I took only 9 of them, but well, in my labs I use it's okay to use 100 zebrafish for experiment.
So hundreds of mines.
Of zebrafish, yes.
You bash the fish on the head, then you cut its brain out, paint the brain, and
Yes.
then look under it under a microscope.
These are the brain. These are the brain of
Oh,
the fish.
can you explain why these pictures?
Guys, still one question. Okay, I mean, we continue, yes, but remember one question. Okay.
What is the difference between the pictures? I mean, why do you need these 3 pictures? Like, the more you laser the brain, the better the result, more precise, or
Not
no?
the better. We hope that, well, according to theory, there should be more damage to the cells. Like, you can see here are the blue ones, the dots here. It's actually just closer. These are the neurons. So the less neurons there are, the more damage the brain is. It makes sense. And we just, we changed the duration of the laser exposure, and we wanted to see how it influences.
Okay.
Thanks.
Magnify.
Sure, you're welcome.
Hello everyone. Today I'm going to tell you about my coursework, and it's called Diamagnetic Probe of the Small Eye Unit. So, what is the main thing about the thermonuclear fusion? Of course, you know that it's plasma confinement. That's why scientists from Butker Institute of Nuclear Physics invented the installation called Small Eye to try the idea of spiral confinement method with spiral magnetic field. But we need to understand: is it really good method or bad? We need to understand it. And there is one characteristic of plasma that tells us, is it good or bad? It's energy of plasma. It's really connected with the diamagnetism of plasma. The property of plasma when it flows, the magnetic fields other directions. That's why we tried to, we created the probe and placed it right there. There is the plasma created and there is the probe. It's not working. How this probe works? So there is plasma. When it flows through the probe, we can calculate the magnetic field of the plasma with the changing the flux that's coming through the loop. This loop, it's our probe actually. And then, according to the Faraday's law of electromagnetic induction, we can get the signal that we then can measure with ADC. So there is our diamagnetic probe. As you can see, its shape is octagon because it's more easier to to create in octagon form than in circle. That's why we just did it. That's a view inside of the unit, as you can see, and my mind is looks good. So there is the signal of our zonde without plasma inside the installation. This experiment needed to calibrate our probe to understand what voltage is connected with flux that's coming through the loop. With that graphic, we get the coefficient, and then with the experiment with plasma in different regimes of magnetic fields of the installation, we just get this graph, and then we calculated the magnetic flux that is measured in Webers, and for straight field, it's 6.5 multiplied to 10 to the power of minus 6 Webers, and the spiral one is 7.3. All this together helps us to understand that the magnetic flux is connected with and the properties of plasma is connected with the regimes of the unit. In future, we will improve the algorithm to make it automatic, to grab the information automatically, and we'll be happy with that. Maybe you have some questions.
Yes.
Uh-huh.
Can you turn back to the
Where?
to the graph to the
What graph? This graph?
Yes. There is a shift in
Zero
value.
This?
Yep.
Then I just take it, took this graph and then integrated it after, because the integral of the signal will actually matter, and this error, then I erased it. You know, no, I can't say it. I mean, I counted it in future.
Is it just a mathematical mistake, not experimental?
Yes, it's a mistake of the ADC.
Alright.
Maybe another.
Thank you.
Is it like okay? Everything okay with it? Why doesn't it work? Why doesn't it work? Okay.
Okay, hello everyone.
Hello.
My name is Semyon, and today I'm presenting my research of azimuthal mode dispersion in cylindrical resonator. So, what was the aim of the research? As you can understand from as you could understand from the title, the aim was to calculate the dispersion, and the objective is just separating this task into some this aim into some basic tests like preparing the experimental setup for measurements, obtaining the data, analyzing it, and getting the results. So at first I want to describe our experimental setup because the way how we did it is more important than actual results. So we always, in our lab, we always use optical fiber in every experiment, and usually we use two optical fibers, two pieces of optical fiber. One as the main object of the research as the resonator. And the second one is we use to excite resonance modes in the resonator. One end of the waveguide we connect to the source of light, another to the detector of the light, and light starts to propagate through the waveguide, and at the point of contact it gets into the resonator and starts to circulate there. The second step was to stabilize our system because it is known that even small shifting in temperature in range, I don't know, from 0.1 to 0.2 degrees can contribute a lot in distribution of our transmission spectrums, and our results wouldn't be credible. So to fix this, we add the additional tunable laser pumping source to our previous scheme. And I don't have much time to explain how it works in details, but it is the fact that with additional laser radiation, our temperature becomes more stable. And even if our system becomes more stable, and even if temperature changes in range of some degrees, our system wouldn't react at all on this shift. So after the experimental setup was prepared, what we did? We calculated the dispersion. As all of you know, the dispersion is the property of media, and dispersion describes how light propagates through the medium, and it describes the light's velocity or direction. In our case, we a little bit redefined the definition of dispersion, but the main point is the same. It's just the difference between transmission spectrum distribution in ideal system without any dispersion that corresponds to these pointed peaks, and our actual one that we got in the experiment that corresponds to the solid lines. So all we did is just measured the resonance frequencies and calculated the distance between solid lines and pointed ones. Also, we took into account that all our optical analyzers have limited accuracy, and to fix this, we approximated our data with Lorentz function, and To obtain the data, we used two different optical analyzers, two different very expensive optical analyzers, and we wanted to compare the results and find out should we overpay our money to calculate the dispersion. Spoiler, we shouldn't. Data that we obtained with the first one, you can see at the figure. The average sign of calculated dispersion is negative. That means that is normal, and the form of these scatters is parabola that coincides with the theory provided by my colleagues before in some clever articles. Second optical analyzer, and the last one, wasn't as good as the first one because, as you can see, there are not enough points to say anything about dispersion because its spectral range isn't wide enough. So this device isn't convenient to measure the dispersion of any systems. Conclusion: the dispersion, as I said before, is normal, and according to the theory, normal dispersion doesn't allow one to generate any interesting nonlinear effects in system, and actually that is bad. That's why now we are contemplating how to fix this and how to create systems with positive dispersion to generate some nonlinear interesting stuff. But this is beyond my coursework. That's all. Thank you for your attention.
This is a direct continuation of your previous coursework, correct?
It's almost repetition of my previous coursework.
But it is different somehow, right?
Little bit, but I didn't have time.
Okay.
Thanks a lot.
Я его закинул. Короче, ладно.
What? What?
Just okay.
Это моя.
Cancer remains the predominant reason of premature deaths all over the world. However, there are many new therapeutic approaches towards healing it, for example, photodynamic therapy. It is based on these core principles. A special molecule called photosensitizer gets injected into the system and then it accumulates at tumor site. The system is then irradiated and photosensitizer converts into one of its active singlet states. Then, through intersystem crossing, it converts into the triplet state. This photoexcited state of PS then can react with triplet oxygen, resulting in singlet oxygen. Singlet oxygen is a highly reactive species of oxygen, and it almost immediately gets involved into various chemical reactions, resulting in tumor cell death. One of the possible PS to implement are phthalocyanins. They have some major advantages like a high yield of singlet oxygen and the absorption peak in a higher wavelength area. However, there are major disadvantages, such as low water solubility. They are unable to selectively accumulate in tumor, and they have a complicated synthesis process. To resolve some of these problems, we shall study a protein called human serum albumin. It has some rather interesting peculiarities. It is a primary transporting protein in our blood. It has an abundance of binding sites with various ligands, but most importantly, it is an effective carrier of PS, making it suitable for being the main transporting agent. In this work, new types of photosensitizers were studied. They were synthesized by our colleagues in the laboratory of Professor Gorbunova. They all have different structures. Which affects their photochemical properties. The aim of my work was to determine the structure of PTs that bind with HSA most effectively, and then to determine their binding sites. To do that, dipole-dipole experiments and computer modeling were implemented, and the obtained data is important, crucial for the further therapeutic use of these compounds. Dipole-dipole measurements were carried out through the technique called laser AMD. Let's say the system has a spin S1, then it gets irradiated and PS converts into the triplet state, hence the second spin appears. They interact through that Hamiltonian from where we can derive resonant frequencies. Now those resonant frequencies are inversely proportional to cube of distance between spins, and that is actually the thing that allows us to measure the distance between two spins. To do that, we in different parts of standard Hunt sequence, we intersect laser impulse and obtain the resulting signal. Parameter delta is called modulation depth, and it resembles the amount of interacting spins. And from this function, we can derive the distance distribution. So these dipole-dipole oscillations were obtained. The modulation depth of 8 beta is 4.7%, and modulation depth of 4A and 4 alpha and 4 beta is 1.5%, which means that 4 alpha and 4 beta bind with HSA less effectively, and the greatest portion of bound PT is observed for 8 beta. Then the distribution function was derived, and to further describe the binding sites, we have to implement the molecular docking simulations. However, 8 beta is a rather complicated system with an abundance of moving parts, and that is why we propose to use another model system, cationic porphyrin TMPP4. They have similar structure and similar distribution. That is what allows us to use this approximation. Now, all the binding sites of all the possible localizations of porphyrin are now presented. These two sites are localized in surface and correspond to two border peaks. One of them is localized between subdomains 1b and 1a. One of them is localized in subdomain 3b. The internal site is a standard for many hydrophobic compounds and corresponds to the middle peak, and it's localized in subdomain SADLO 1. So in this work, a new approach for studying HSA-PS complexes was applied. It was discovered that 8 beta binds with HSA in 3 sites, and 4 alpha and 4 beta are less effective in binding with HSA.
Could you please return on the second slide? It will be fast.
So.
How we should pronounce this underlined word?
Phthalocyanins.
Follow what?
Phthalocyanins. Phthalocyanins. Phthalocyanины.
Localization.
So rabbits that jump around tomographic center have cancer.
Not really. Well, we mix HSA. First of all, we selectively introduce intractide spin label into cysteine 34 of HSA. Then in that solution we put the studied phthalocyanin. The solution is frozen and placed into ESR spectrometer Bruker EMX 580. Because you can't carry out those experiments at room temperature. since the full-dipole oscillation would just.
Time waste for no one.
Oh,
Ставь флешку.
Втыкнуть этот пультиком.
Что?
Синий провод втыкнуть в флешку от пультика.
Перф.
Флешку от пультика попробуй вставить в этот синий провод.
Нет,
Нет, флешку от пультика.
Сперва скинь, потом...
Коротенькая, видишь? Маленькая.
Давайте без этого.
Окей.
So, the theme of my proposal was modeling the kinetics of combination of charge carriers of perovskite in different temperatures. I know it's quite impressive. So, what did we study exactly? These things are called perovskites. They are believed to be a new world in the world of photoelectronics because they are cheap to produce, and mostly because of their unique photoelectronic properties. They got very charge carriers in them with very long times and so on. So nowadays it is the studies achieved the efficiency of the peak efficiency of the use about 24%, which is huge. However, it is already surpassed the devices that we used before. However, the various calculations shows that their peak efficiency can be higher, around 30%. And which means that we still do not understand what is happening, what combination events happen there. The most novel approach to this problem was the so-called standard shock rate called theory. It was developed in our lab. However, we still have some researchers still have doubts about its possibility to devices at different temperatures. That was the theme of my proposal. To study them, our esteemed colleagues at Lund University in Sweden, they measured the photoluminescence of previously prepared perovskite films. For this, they used the specially constructed strap, which consisted of pulse laser and two different types of measured devices. One of them measures the decays of photoluminescence in time, and the other one just measures the dots. Here you can see the result of this, how exactly they measure, how exactly they conduct their measurements. To show the results in the correct form, to study them, we use logarithmic scale on the both sides, and this mystical word PLPA stands for photoluminescence quantum yield. It is the relation. It is the amount of photons that our film absorbed divided by the amount of photons it's related emitted. It shows the efficiency of inner movements. So the result that they got were these two graphics. In the first one, we can see they are measured by the different temperatures. In the first picture, which is the metal perovskite at 290 kelvins. And about this film, we know a lot. We studied them using different theories. We know almost everything about it. We know all pneumatic constants about it. However, as for this one, as for the same film at 77 kelvins, we know almost nothing. And that's why we tried to use our theory to apply it to this unusual situation and to study about it. So, to do this, we used, as I mentioned before, standard shock rate Hall theory. What is all about? as you all know, in semiconductors there is a valence band, there is a conducting band. When we excite our semiconductor, there are population of 3 electrons and 3 holes are created. And however, in some semiconductors, such as perovskite, there are not only valence and conduction bands. There are, due to some imperfections, because we are using metal organic devices, there are so-called trap levels. The event of ionization through trap levels is more likely due to the fact that this energy gap is around 2 electron volts, and it is evident that it is not likely to need such high energy at the time. So, if we will note all imaginary lengths as constants, we can obtain such experiment. A system of differential equations, and this is what the SRH series was about. So, to study its applicability to the general things, we created a computer model, and we, as you can see, to the subject you know a lot about, it is perfectly applicable, which is the dots are experimental data, and the lines are what we calculated or simulated. As for then, we, by empirically estimating some constants, we were able to produce this result, which is the same low temperature device. However, you can see the theory was able to describe it, to simulate correctly, and the correlation between theoretical and experimental results proves that the theory is correct and it can be applied to films at any temperature. That means that, however, we still, because we need to use empirical estimates, we still far from the complete description of the combination of all combination events in perovskites, so we need to study it more. That's all. Thank you for listening. Any questions? Any question?
I have a question. Can you open this red slide? Why do they need microscope in this scheme?
I suppose because
We have microscope.
it is an excellent question. You see, the films that we can produce are really small, and they are around 150 nanometers, something like that. And to verify that they really produced what they produced chemically was a perovskite, not some ions compound, they just looked at it through the microscope. So the sample, the general microscope that they have to verify that this structure is really perovskite.
Is there a folder that you could put this in?
Just open it, I guess. That would be enough.
Yeah, so I apologize in advance. I haven't had any sleep for like 2 days, so I might be a little bit sleepy. So today I'm going to present to you my coursework, which is modeling of measuring coil systems with damping properties, which is a name that is definitely not easy to pronounce. And my presentation plan is going to be as follows. I'll have you know my goals. Then I'm going to have some theoretical introduction, which you won't even listen to. Then I'm going to show you the modeling and the results, and then I'm going to say that I'm actually a good scientist. So for the goals, I'm required to write a program to model magnetic fields. Then I should use an optimization algorithm to find the optimal solution for the compensation coils parameters for quadrupole and sextupole fields. So the theoretical intro, don't look at this. Basically, what it says is that when you have a coil and you rotate it inside a magnetic field, it produces a current. Blah, blah, blah. The current can be shown as follows. Then straight to the modeling part. So what I need to model? I need to model a field that is represented as a quadrupole or a sextupole. This is the part of the code that does that, and on the right you can see the graphs that it made. The top graph is the quadrupole, and the bottom graph is the sextupole. The sextupole is a little bit funky, but all in all it's okay. This is the part of the code that models the signals from the coil. So when you rotate a coil inside of a field like this, it gives you a sine wave. And this sine wave is what I model, basically. So yeah, here you see a coil, this little thing that is like not related to anything LGBTQ, but it's just different colors. It's one coil, and you rotate it around the axis that is literally there, like the center point. And you get this signal, which is a sine wave, like it should be. So everything's good. Now, the hard part comes when I need to model a specific kind of coils array. So these are 3 coils. They are attached to one another in a specific way, so that the main field, which is the quadrupole, as you can see, this is the quadrupole field, is dampened enough so I can see the small sextupole field that is actually present. So when you look at the graph of the field, you cannot see that there is a sextupole component, but it is there because I modeled it. And the point is to make such an array of coils that you can see it. And as you can see on the right graph, the top graph shows the signals from the yellow graph is the signal from this coil, which is not present here. And the blue graph, which is, it looks like a straight line, but it's not, is the graph from these 3 coils. And then on the bottom graph, you can see the enlarged version of the blue graph. So the blue graph is a quadrupole with a sextupole. So you can see the components being added, which is good, because that means that the quadrupole is dampened enough for us to see the sextupole component. This is the Fourier transform of the graphs here. So the yellow one is the yellow one, the blue one is the blue one. The yellow one, unsurprisingly, shows that there is only the second component, the quadrupole component, and the blue graph shows that there is actually a sextupole component near it. Near the number 2, there's a number 3. So this is a screenshot. I cannot like change it. So the results are just a big graph of exact coordinates of the coils that need to be put. So it's nothing too interesting, but yes, I did this basically for the quadrupole and for the sextupole. So in conclusion, we, aka I, developed a software for modeling signals from rotating coils. We, aka I, found the optimal parameters from the dampening of the quadrupole field and the sextupole field. And the software is ready for further development. Before anyone asks any questions, we actually created these coils. So like, we took this, we put this into a company that makes coils. And when we tested it, it did not give anything like what I calculated. It was absolutely not this. Absolutely not this. It was so bad that I think I'm going to be fired soon. Any questions?
Yes, what was the reaction of your supervisor when...
Oh my god, I still ignore him. I think he hates me. Honestly, he was calling me every day, and I was on vacation. And he was calling me every day, and I didn't pick up, and then I came back, and he was like, "Where have you been?" I'm sorry, don't kill me. Yeah, luckily I have a friend at work that deals with all my problems, so she did everything for me.
Fine.
I overheard everything.
Thank
That's
you.
it.
Hello, my name is Kate. I'm from the Quantum Electronics department, and I'm going to present you my coursework for this semester. You all know that magnetometer is a device measuring the magnetic fields, and the optical magnetometers, which we develop in our lab, have some advantages in the field of measures big magnetic fields compared to the other types of magnetometers. And my research goal was the research of Harmonic resonances in rubidium atoms in special cell, and study these applications in magnetometry. Well, what is Harmonic resonance? It is increasing of light transmission through the medium in the raw magnetic fields. If we have transverse magnetic field and circular and light with circular polarization pass through our cell, in the magnetic field, lower sublevels of atoms will be coherent, and atom absorb the energy from light beam. When in the zero magnetic field, this connection destroys, and electrons pumped in sublevel which isn't action with light, which has no action with light, and the cell became transparent. If we have a linear polarization in the raw magnetic fields, atom transfer into the coherent population trapping state, and medium again became transparent, but the magnetic field destroyed the state, and we see the resonance. So to research our resonances, we have this experimental step. We use laser with wavelength 795 nanometers, cell with rubidium 87, and nitrogen with pressure of 300 torr, and we modulate magnetic field, transverse magnetic field around the cell by Helmholtz coils. So we obtain the Harmonic resonances on different temperatures of cell and different power of light beam, and after data analysis, construct these graphs. It is the dependencies of sensitivity of our magnetometer to temperature. Sensitivity is a minimum variation of magnetic field which our device is able to detect. and it calculated how ratio between width of resonance to signal noise ratio. So on this graph we can see that magnetometer have optimal temperature to work. It is 80 degrees, and with increasing of power of light beam, the sensitivity enlarged. Also, we have experiment with polarization, ellipticity, and this graph shows dependence amplitude of polarization. The highest amplitude we have with circular polarization, and in with linear polarization we have no resonance, because in our cell buffer gas pressure is very high, and it make high levels of atom merge. So in this system exist two CPT states which compete, and because of this, atom still absorb the energy from light in zero magnetic field. So we see no Handley resonance. In conclusion, with these optimal parameters of our magnetometer, we could obtain the sensitivity on the level of nanopascal. Thank you.
Was the new magnetometer, I thought that maybe these parameters are usually in documentation to some these magnetometers or whatever.
No, the method is very old. Handley resonances field research around 100 years ago, but the new of this system is cell, because buffer gas pressure is very high, and it produces some new effects.
So this is a new magnetometer, right?
Yes.
Okay.
Okay.
I'm Sonia, and in my coursework I study influence of different ions on thermostability of different types of nucleic acids complexes. So what do we know about nucleic acids? Nucleic acids are natural polymers that consist of nucleotide, each and every nucleotide consists of ribose or desoxyribose in case of DNA, nuclear base, and phosphate moiety. Primary structure of nucleic acids you can see in the slide, and nucleotide interact with each other by oxygen bonds. Nowadays, it's become possible to modify nucleic acids, but some of them have disadvantages. And I want to tell you about one of the coolest modification of nucleic acids, and I want to study the behavior of native and modified complexes in buffer with different concentration of magnesium and zinc ions. I use this model system where H means native structures, FG means phosphoryl-guanidine modified structures. Data was received by thermal denaturation method with optical registration of signal and principal scheme of spectrophotometer you can see on the slide. And also we use two-state model to calculate melting temperature and different thermodynamical parameters. As a result, we have integral curves for each kind of ions. And in case of native structures, we can see a shift of the inflection of the curve when we increase the concentration of magnesium ions. More clearly, the result of experiment we can see from differential curves. Also, we can see a shift, but in case of modified structures, we can see that melting temperature increase insignificantly. The same differential curves there are the same differential curves for zinc ions, and as we expected, we can see a shift for native structures, but we were surprised that we can see a shift also for partially modified structures. But I want to pay your attention that increasing of temperature in case of modified structure is less than in case of native. So this study show that our assumption about divalent ions stabilizing DNA complexes was correct, and magnesium and zinc ions interact with DNA complexes in different ways, and these and the following studies can be used in diagnostic and gene therapy. Thank you for your attention.
No questions, great, excellent.
We're speeding up.
No, there's no question.
Hard. Chemistry.
This is the theme of my presentation and my coursework. I'm Selena Bayer from the Institute of Automation and Electrometry and from the Department of Automation for Physical and Technical Research. So firstly, I would like to tell about the problem around which the whole coursework is spinning around. And so imagine that a lot of people are watching translations, TV translations or the translations in the internet, and they require high speed and good quality from the data or from the media content they are watching. And so for this, the developers have developed a lot of technologies and protocols to overcome this, to fit these users' requirements, and everything is ideal until the data is not lost. And I would like to tell us that if the data is not transmitted through the network in one step, like the movie, and the data is cut into little pieces like packets, and further I will tell about the packet loss. So when the packets are lost, the reason for this can be the stream overload, like there is a limited buffer that is processing the data, and when it's overloaded, it just rejects some of the packets that come to the receiver. So we have next consequences when we lose packets, like data loss, drop of speed, video or audio quality degradation, and delay of media content or the stop of the translation. And so, what is the solution for this problem? Using protocols that guarantee low packet loss. Like in 1990, there was RTP, and nowadays one of the most popular solutions is the SRT and RIST. RIST is not popular. It was developed recently, like in 2019. And my presentation is about the RIST and my coursework. And SRT and RIST, they are having a lot of things in common, but RIST provides some advantages, like the support of IPv6. It's the Internet Protocol version 6. It also supports packet filtering, and it supports multicasting. What is multicasting? Multicasting is when there is one sender and a lot of receivers. SRT supports only one point-to-point connections, like sender to receiver only. And for this, this is the reason why RIST is practically interesting for use. So there is a problem that this protocol does not have a good documentation. And so what is RIST? It's a transfer protocol. It is designed for reliable data transmission. It recovers lost data and supports multicasting. And how the packets are recovered? A lot of protocols need the packets. As I said before, the data is transmitted in packets, and in some protocols like TCP, all the packets have a consequence number, like first, second, third. And on the receiver side, the receiver checks whether the consequence number is the next value of the previous one. Like the previous one was the second, and the third one has to be the third. And if the packet that came to the receiver is fourth, it just asks for the sender to retransmit the lost packet. And for this, and in TCP, for example, for each packet, the receiver sends an acknowledged number to the sender. Like, I have received the packet, I have received the packet. And if he lost the packet, he sends I have lost the packet. And it's very small or it's very slow when we use TCP. And so in RIST protocol, he does not require to send acknowledges for the packets that received correctly. Like the packet is received, no need to send to the sender any information about it. And if the packet is lost, he sends the number that says that he lost the packet. So that's how we just increase the speed of the connection. So the whole goal of my coursework is to develop a test stand, which one can be used to test the noise immunity of the library. As I said before, the library was released in 2019, and it has bad documentation. Like every question I was having when I was working with this library led me to the developer's site where they said everything is good, and no users were asking some questions about this library, and so I had to check all the files in C, and it's very hard for me because some reasons. So there is a resender, bitrate, and packet loss. And with receiver, I have developed two applications. The bitrate is the speed of the connection. It's like, I say 100 kilobytes, and he sends the packet, and then if the packet is received, he just check. Does he need to sleep a little bit of time to send the next packet or not? And if he does not have to sleep, he just sends the packet immediately. And if he has to sleep, he just sleeps for some milliseconds. So this is the result of my working program. The results, I understood the basics, the test stamp was built, and learned some information. Thank you.
I have a question. Firstly, you said that the RIST library was made in 1990, but then
No, I've said the RTP 1990.
But 20 years later, here comes RIST with bad documentation.
No, in 1990 there was a protocol. Its name is RTP. Due to various reasons, like the improvement of technologies, this protocol is old nowadays. And nowadays, one of the most popular solution, is the ASRT, Secure Reliable Transport. But as I have said, there is three disadvantages, like it does not support packet filtering, does not support IPv6, and does not support multicasting. RIST have solved these problems, and but as I said, this library is new, relatively new, and there is a bad documentation written for it. And for this, my coach told me to build a test stand and to check whether this library is good for the usage, like the noise immunity. It's to test the noise immunity of the library. And my coach is working with TV or media translations, and this is the reason why he wants to check whether the library is good or not.
So, hello everyone, and this my term paper presentation is detecting and visualizing trends on the coastal profile. So today I will not show you any hard physics. There will be some simple math algorithms and a lot of pictures. So here's my plan. We'll take a look at the depth profile in 3D. We'll convert somehow a 3D profile into two-dimensional, and then I'll demonstrate the algorithms that I developed. Firstly, it's a segmentation algorithm, and secondly, it's a trend detection algorithms. So, why do what is trends, and why do we need to detect trends on coastal profiles? So actually, if anyone wants to build something near shore, for example, you want to build some kind of canal, or you build a construction, and you want to be sure that how the depth profile near shore apps and you want to be able to predict how it would evolve. I mean, what would be sediments, how would the sediments act? Would they contain or would they erode? So, there are some models, mathematical models that predict depth profiles, and to make them better, we want to determine and to be able to detect depth trends. So, okay, finally some pictures. So, here's important moment. We're working with one-dimensional profile. Here's this. And if we take depth measurements of one-dimensional profile for several time points and then combine them together, we'll have something that looks like the image on the right. Please take attention that it's not spatial coordinates. One coordinate is spatial, it's z, it's distance from the coast, and the second coordinate is time. So this is the data that we'll be processing, and so we want somehow to be able to extract segments and trends in profile spatial and temporal evolution. So what did I decide to do? I decided to convert a depth map into a two-dimensional picture and to code a depth level by a color of a pixel. So on the left side we can see the same profile, but in a two-dimensional representation, and its original representation, and on the right side we can see a smoothened representation that is quietly easier to understand for humans. And what a segmentation algorithm I developed. So I decided to take a look at two pixels that are located nearby, that are neighbors, and if they have relatively same height level, then I will combine them. That's really simple, and that's what we have. We have some segments like an original representation and smoothed representation, and about trend detection algorithm. I'll better show you pictures right away. So first thing, to detect trends as a direction where a segment, a depth profile segment goes. So to detect the direction, firstly I wanted to use a simple linear regression over all points of extracted segment. On the right bottom you can see example of such extracted segment. But then while testing on the some testing data sources, I realized that internal points of a segment are not as important as points on sides. So I just took an average from a point from the beginning. I took an average from points from the end of segment, and then I combined them together below. So that's it. We did it to the end. During this course work, I have developed segmentation and trend detection algorithms, and they will be used they can be used to provide more precise depth profile prediction models. So that's it.
How precise is your trend detection? Did you test it on actual results, actual maps?
Well, everything that I did and every picture that I shown to you, it's real data that has been processed. But well, actually, the only way to determine how good the trend detection works is to perform segmentation and trend detection on many source profiles and to check them like by yourself, the visual aspect. So do you consider it works good or not? And these algorithms works pretty good.
Hello guys, my name is Anna, and my coursework consisted in studying the reaction of boron isotope with protons with emission of 3 alpha particles. And the reaction is really important in diverse fields. This is important for proton therapy of cancer, for thermonuclear fusion, and also for nuclear astrophysics, and so on. Today I would like to tell you about the reaction, about aims and steps of the coursework, about the experimental facility where the experiment was conducted, the results we obtained, and we will come up to the conclusion. Well, when a proton interacts with the boron isotope boron 11, it creates a carbon-12 atom in an excited state. The carbon then breaks up in an alpha particle and in a beryllium-8 nucleus, which in turn decays in 2 alpha particles. If beryllium-8 produces 2 alpha particles from a ground state, then the reaction happens in an alpha-0 channel of the reaction. And if the beryllium creates 2 alpha particles from an excited state, then the reaction happens in an alpha-1 channel of the reaction. And please pay attention to it, that is important. And what is the problem with the reaction? The scientists have been studying the reaction for already almost 90 years, and the existing accumulated data are discrepant. On the screen you can see data from the nuclear reactions database bundle, and the cross sections. That is how cross sections depends on incident energy of the proton beam. The cross section, the data is were detected at angles that are close to 135 degrees, which is the focus of the present work. And pay attention to small energies up to 2 MeV, because they are the focus of the present work. And steps to the coursework. The aim of the coursework was to acquire new knowledge, to update and specify the preliminary studies dataset in a range of energies 0.3 to 215 MeV. to achieve our aim, we had to irradiate a thick boron target, a thick boron-containing target with protons on vacuum-insulated tandem accelerator at beam, and to measure the spectrum of alpha particles, and to simulate the proton beam and the boron-containing target interaction in the program. So let's take a closer look to our accelerator, where we irradiated our boron target. First, there is a negative ion source, where negative ions of hydrogen were created, and then they were focused at the entrance of the accelerator, where the positive potential applied to the central electrode accelerated the negative beam to energy of energy E, and then the protons protons arrived to the central electrodes, to the gas stripper, where the 95% conversion happened, and negative ions were converted to protons. Then the same potential accelerated protons to energy 2E, and then we can or bend our beam with the help of a bending magnet, or we can just make it travel forward to our boron target. Boron target is a boron carbide plate, which is 4 millimeters thick, and it was placed on a cooled copper substrate and was set at the target assembly. That is just a picture of how all it looked. You can see the first one is the alpha spectrometer, which measured the alpha particle spectrum. This is the target, exactly where the plate is. And these are 4 spectrums, 4 typical spectrums of alpha particles and backscattered protons. The dramatic shelter, which is here, up to 1,000, we can interpret it like the elastic scattering of protons from boron and carbon. After that, we can see this smoothly flowing shelf, which we can interpret as the alpha 1 channel of the reaction, and this little coming rise at the end with 2,000 keV, which is one of the highest energies. We can interpret this little peak like alpha 0 channel of the reaction, and also the simulation was performed. And apart from carbon and boron, we revealed that the target also consists of little bits of iron, oxygen, and manganese, which is caused by the manufacturing method. And that is the spectrum. Blue one are simulated data, and red ones are experimental data, and they fit really good. And well, what we got, the reaction occurs. The reaction has 2 channels, and this is agrees with the present, with the nowadays conceptions. We succeeded to reveal the accurate composition of our target, and in future we plan to study thin boron target in order to measure the cross sections of both channels of the reactions. Now I'm ready to answer your questions.
Thanks a lot. Yes, thank you very much. Could you please go outside, wait for a second? We need to discuss your results with a colleague, and we will invite you in just a moment.
Да, блин, тоже.
На онлайн? Я думал, вы запись ведете.
Да нет, запись.
Да?
Это просто запись.
Да?
Да.
Все получилось?
Да.